JF-17 Thunder is a very interesting project for two reasons. One, it shows what can be achieved with an incremental development approach. Two, from a technology point of view, it features a surprising detail that is very useful to explain how supersonic propulsion works. However, I'm running ahead of me, so let's start from the beginning. Welcome to Millennium 7 Star, the channel that helps you make sense of military history and military technology. Please stay with me till the end, because the stuff that we discuss here is not easily found anywhere else on YouTube. The origins of the JF-17 are quite complex. In the second half of the 80s, the Pakistan Air Force was in search of a replacement for its aging fleet of Mirage and Chinese replicas of Russian planes. In the same years, in China, Grumman was providing its expertise to design a new and modern fighter based on the Chengdu F-7, a Chinese copy of the MiG-21. Both projects were abandoned because of international sanctions, but China was determined to progress in its efforts. In 1995, China and Pakistan signed a Memorandum of Understanding for the design of a new multi-role combat plane, splitting the cost and engaging with the Mikoyan Design Bureau to provide extra design expertise. Pakistan was going to equip its air force with about 150 units, while China wanted a cheap alternative to Western designs for the export market. The development of the plane went through the usual vicissitudes of every development. In 2001, the avionics design was decoupled from the aircraft to keep the development going, while the avionics were sorted. The maiden flight happened in August 2003, and the flight trials brought to light some problems as usual. The leading edge extension routes had to be altered, the vertical stabilizer was enlarged, and a very interesting design of the air intakes was adopted, the diverterless supersonic intake, which is becoming a landmark feature of Chinese projects. Production started in Pakistan in 2007, assembling Chinese-built kits. Afterwards, while the final assembly happens in Pakistan, parts production is split between the two countries and Russia. The Pakistani Air Force has about 100 JF-17 in service. Myanmar acquired 16 planes, and an undefined number has been ordered by Nigeria. China seems to have no intention of acquiring the plane, which is designed and produced for export only. The variants in service in Pakistan are Block 1 and Block 2, while the Block 3 is in its initial test stage as we speak. The JF-17 is a multi-role combat aircraft on the light side of the spectrum. The empty weight is about 6,600 kilos. The maximum takeoff weight is 12,700 kilos. The payload amounts to a relatively modest 4,600 kilos, albeit it is about 36% of the maximum takeoff weight, which is just slightly low for the category. Thrust-to-weight ratio calculated with the plane at the maximum weight and no afterburner is about 0.4, aligned with other modern medium-light contemporary fighters. The construction is very traditional, making large use of aluminum and other metals, arguably to keep the cost low, even if some composites have been used on the Block 2 aircraft. According to some sources, the airframe has a useful life of around 4,000 hours, which is about a third of modern Western designs, despite the fact that the maximum load factor is limited to 8 Gs. The MiG-21 heritage is not easy to spot. Perhaps the fuselage with its spine and the cylindrical shape that doesn't follow the area rule is still bearing some similarities. But everything else seems to have changed. The iconic nose intake has disappeared, but probably the most important update is the completely different wing and tail, if compared to the MiG-21, that make the JF-17 basically a completely new plane in terms of performances. Seen from above, it reminds quite closely the design of the F-16. The wing is very thin, like on the F-16, and it is quite small, proportionally smaller than the F-16. It has a classic swept leading edge and a straight trailing edge. It is an effective solution, almost as good as conventional swept wing for supersonic flight, while the long root chord helps increasing the surface for the same wingspan and allows for a very stiff structure. Some sources call it a prop delta, but it is not. The sweep is too low and a delta wing doesn't need the large leading edge root extensions mounted on the JF-17. The confusion is probably due to the presence of the automatic maneuver slats and flaps, which are often seen on modern deltas. We have an entire playlist discussing how the delta wing is actually working, so if you are interested, it is definitely worth a visit. It would be interesting to understand why the Delta Plus canal configuration was not chosen, also considering that China has an excellent experience with it acquired with the J-10. My guess, and it is a guess, is that we are seeing the heritage of the MiG-21 shining through. If the fuselage is derived from the MiG-21, adding a delta wing and the consequent area ruling would have meant basically a complete structural redesign. The plane is unstable in pitch. The original design included a fly-by-wire control in pitch only, with mechanical controls in roll and yaw. The production solution has a 4 redundant channel fly-by-wire control in pitch and a dual-channel stability augmentation system applied to the mechanical controls in roll and yaw. Adopting a fly-by-wire control along a single axis is quite a strange choice, because all commands are actually coupled. If the plane rolls deflecting the ailerons, the asymmetric drag makes it a yaw 2, which is compensated in turn by the rudder on the vertical stabilizer. The roll also tilts the lift vector, so if the plane doesn't want to lose altitude, it must increase the lift by increasing the angle of attack by pitching, and so on. This is called command coupling and is perfectly normal. Modern fighters do not require the pilot to use all the commands at once, but they just receive an input and the computer maneuvers the plane to execute the command. A single computer-controlled axis might help in keeping the plane straight in pitch, but it won't do anything to prevent a spin departure, or limit the G-load to preserve the structure, or recover the plane in case of the pilot passing out. I also suspect the fly-by-wire system can move the stabilators asymmetrically, even if the conventional commands in theory could. The propulsion is assured by a single Russian RD-93 turbofan, a derivative of the MiG-29 engine, providing a thrust of 50.4 kN dry and 85.6 kN with the afterburner. The engine has a digital control unit, but it's not a full authority device. This should mean that there should be still a mechanical connection with the throttle. In an era of FADECs, the choice can be explained once again with the desire of keeping the cost low. The upcoming Block 3 variant might use the Chinese W13 engine with more powerful and with a longer lifespan. However, Pakistan has confirmed that it will keep using the RD-93 to maintain a logistic uniformity. Anyway, there is one feature of the propulsion system that is really outstanding. The JF-17 intakes are diverterless supersonic intakes, a simple idea derived from a principle that had been known for decades. The first to design and test a working DSI was Lockheed Martin in the early 90s, but since they are relatively easy to copy, they are becoming more and more common, and the Chinese really embrace them. At subsonic speeds, air intakes are not particularly complex. The complex geometries that can be seen on fighter jets are there to cope mostly with high subsonic, transonic and supersonic flight. This subject is vast and it is worth many videos in itself, but now let's try to qualitatively understand how do they work. The main function of air intakes is to recover pressure. That is to turn the airflow kinetic energy into static pressure at the entrance of the engine. The higher the pressure at the entrance, the higher will be at the nozzle, where the subsequent expansion will produce thrust. At high speed, there are two problems that can greatly reduce the pressure recovery: the boundary layer ingestion, and at transonic and supersonic speed, the formation of shock waves. So the boundary layer is a layer of slow-moving air sandwiched between the aircraft's skin and the free flow. Since it is slow-moving and often turbulent, it doesn't have much energy to convert in pressure. This is the reason why almost all the jets from the late 50s onward have intakes separated from the fuselage by a slot a few centimeters wide. In this way, the boundary layer and the slot, and not the intake. The shock waves form at transonic and supersonic speed. They are thin surfaces where the flow condition abruptly changes across. The flow in front of the shock wave is supersonic, while the flow behind the shock is slower and potentially subsonic. The problem with the shocks in respect of the intakes is twofold. One, the more the shock is strong, the biggest the change of speed and pressure, the more waste of energy there is affecting the pressure recovery. Two, if the shock enters the intake, it may bounce off the walls and reach the engine compressor, where it can disrupt the flow to such an extent to limit the engine thrust, or even create vibration and ruptures. To obtain a weaker shock and control its position, air intakes have been equipped with mobile cones, ramps or wedges, whose purpose was to generate an oblique shock weaker than a straight shock and control its position. All these devices have been working well for decades, but the DSI may be considered an improvement. If we place a smooth, elongated bump in front of the intake, the frontal surface of the bump acts as a compression surface, and in supersonic condition, it will generate an oblique shock. The effect of the compression, though, will be such to force the boundary layer on the side of the bump and away from it. A new boundary layer will form on the bump, but it will be much thinner than the boundary layer that began developing from the nose of the aircraft, hence it won't subtract much energy if ingested. The ESIs are often slanted forward, like on the F-35, to let the deviated boundary layer bleed from the sides. Since the SIs do not have moving parts, they really can't control the position of the shock, but the proper shaping of the bump can greatly reduce the strength of the shock, basically making it thicker and mitigating the problem. Just remember the term isentropic shock for when we are going to discuss the intakes. The SIs have a sweet spot in which they behave at their best, and they lose efficiency at lower or higher speeds. The key point is that, in practice, the sweet spot can be between Mach 1 and Mach 1.3, where the pressure recovery improvement against an intake with no bump can be up to 6 or 7%, while the performance above and below are basically the same as a normal intake. An intake with a mobile device could be more efficient in a larger range of speeds, but the DSIs are way less complex to be designed and built, they do not require a control system to be operated, and they are much lighter because they have no moving parts, and the drag they generate is even slightly lower. In modern fighters, where speed is less than a concern that it was in the 60s or the 70s, they are not a disadvantage at all. No surprise that they have been chosen for the F-35. There is also a final consideration. The bump on the intake is partially screening the engine compressor, which is a very strong source of rudder returns, and the intake itself is more stealthy than a conventional intake. There are fewer lines and surfaces that can reflect the radar. The Chinese adopted them on various planes, including the J-10, and it's no surprise that they have been chosen for the JF-17 too. it is difficult to understand exactly what type of avionics is installed on the JF-17 because it seems that every block starts with a great ambitions that are scaled down further down the line. From the information we have, the JF-17 has a modern avionics suite, mostly of Chinese origin. Like many other modern jets, the avionics software is based on an open architecture and is developed in C++ language rather than the usual military ADA. This is another measure that may reduce the cost since there is a much larger C++ programmer base. There have been many contacts with Western manufacturers, but in the end nothing seems to have materialized. The plane had, since its inception, a glass cockpit with multifunction displays. Block 1 planes had the radar, the electronic warfare and the defensive suite with the radar warning and missile approach warning, but there was no direct data fusion. Block 2 planes added a secure data link. Block 3, other than a general and secret improvement of the electronic warfare suite, is expected to support an AESA radar, an infrared search and track, which was on the wish list since Block 1, and a helmet-mounted sight, plus a single large touch display like on the J20. The really interesting feature, though, is the fact that the black boxes talk to each other on a MAIL-STD1553 network, and the hardpoints are wired with MAIL-STD7060 standard. This choice makes it a lot easier to integrate Western equipment with the plane. For example, a Turkish-made targeting pod has been acquired by the Pakistan Air Force and integrated with JF-17 with no particular issues. The plane has 7 hardpoints, 2 wingtip rails for the air-to-air missiles, 1 on the center line and 2 under each wing. There is no dedicated hardpoint for external pods, and this will detract from the already scarce hardpoint availability for the air-to-ground. Considering the relatively modest maximum weapon load, the plane is squarely on the light side of the attack category. The limitation may not be so relevant for air-to-air combat, where a full panoply of Chinese weapons is available. For Block 3 aircraft, however, Pakistan is trying to integrate a modern Western missile like the Darter or the Iris-T. An interesting feature is the availability of anti-ship missiles, something that is no longer common on non-naval aircraft today. So where can we place the JF-17 in the modern landscape of combat aircraft? Well, it is a light and simple multi-role combat plane with an emphasis on light. It is a relatively small and light jack of all trades and master of none. It is basically a Chinese plane, even if the technology is slowly being transferred to Pakistan, demonstrating a pragmatic approach to the problem of providing the Pakistani Air Force with a low component of the mix, where the F-16 is the high component. While this may seem rather uninspiring, the plane has a very important strength that might cast a different light of its place in the world of air forces. The JF-17 is a lot of bang for the bucks. It may well cost less than 1/2 of a used F-16 and way less than a Gripen, but definitely packs way more punch than half of an F-16. This means that it can be the ideal machine for very poor air forces who need a limited number of higher performance planes, becoming in this case the high component, or it may enable larger air forces to pursue quantity rather than quality doctrines. This is an approach that has not been applied since the fall of the Soviet Union, and trust me, it may be attractive in some cases. Either way, I have to admit, in the JF-17 there is much more than meets the eye. So if you like this video, I'm sure you will like also the videos that are going to appear beside me. In the meanwhile, please like, dislike, subscribe and hit the bell so you won't miss anything. And if you could consider supporting the channel on Subscribestar or Patreon, that would be amazing. In the meanwhile, thank you very much for watching, stay safe, and see you next time.